Learning outcome 7 first of all. But I was going to bundle that together with 8. Right, so 7 and 8 we're going to do together. And that was what is meant by diffraction. What are the limitations? What are the effects of wavelength on diffraction? So first of all, what do we mean by diffraction? The diffraction is a bending of a wave around an obstacle or through a gap. So longer wavelengths diffract more than shorter ones. So if an object is small, the large wavelength will bend round it and it cannot be detected. So small wavelengths are needed to detect small objects. And the last wee bit, if a gap is small compared to the wavelength, significant diffraction occurs. In learning outcome 9, we'll look at the different diagrams that you could ask to be drawn. So we'll start by kind of just putting a box around the area that we're interested in. And then we'll do a few different selections. We're going to put an obstacle in the way of this one. And then look what happens at the waves as they travel around it. Now these diagrams are known as plan views. We were looking at the view of the wave from above, and each of these lines represent the crest. So we've got these nice regular waves approaching this obstacle. Regularly spaced, constant wavelength. And then what happens next? What we have is the idea that the waves above the obstacle will continue unaffected. So I'm just going to draw a dashed line in there. And then we've got the idea of diffraction, that some of the wave will bend round. I'm going to draw another diagonal line there to show where I'm going to put the waves bending round. So above this dashed line, nice straight line still for our waves. Unaffected. Same constant wavelength. Diffraction doesn't have any effect on wavelength, frequency or speed. And then what we have to draw is them bending round into that region there. And that's diffraction. Now, what differences could we see for different diagrams? Well, you could be asked to look at the difference between, say, shorter wavelengths that we've drawn there and longer wavelengths. So below this one here, I'm going to put another diagram, and draw my box again. I'll just fill this in, I'll pause. So the exact same idea as before, but this time I'm dealing with a longer wavelength. I'm going to make it double the wavelength. So I've only got a crest kind of wider apart than there were roughly every two that there was before. Same dashed line goes along the top, waves above that will continue unaffected, and then we'll have diffraction occurring again, but what we want is the idea that with a longer wavelength you get more diffraction, so that second dashed line goes at a steeper angle. But then we'll once again draw the same wavelength continuing, and then we've got those longer kind of circular arcs, and that's for a longer wavelength. So we'll label them, and then we've got one more diagram we need to draw. So shorter wavelengths, diffract less, longer wavelengths, diffract more. And then last, if we look at a diagram of going through a gap, similar sort of idea, just a wee box here to define the area that I'm interested in. And think of this as the ripple tank that we used in class to study the waves. And this time I've got an obstacle above and an obstacle below, i.e. I've got a gap in the middle. And I've deliberately drawn nice long wavelengths for this one, because I want to emphasise that point. That when you have a long wavelength going through a gap, which are much smaller than it, then what we get is significant diffraction. Right? Almost semicircular wavefronts. So these lines are going to be quite steep, and then what we've got are these semicircular sections. Not so good at drawing freehand, but that's the sort of idea. So long wavelength, going through a gap which is smaller than that wavelength. Leads to significant diffraction. Almost semicircular.